Okay, we are doing notes number 18 today, simplifying radicals. And if you remember from our last lesson when we were doing factoring, at the end we solved equations by factoring. And so the point of reviewing simplifying radicals today is because some of the quadratic equations we're going to solve, we're going to use radicals in there. So I start with a question, are these the same? If I use the words and ask you for the square root or square roots of 25, or if I use the symbol square root 25, are these the same? And the answer is no. So if you're using the words find the square roots, it means just find whatever numbers you could square to get 25. And so you could square 5 to get 25, you could square -5 to get 25. So there are two answers to that. However, when you see the square root symbol or the radical sign, that means the principal root. I think it's this spelling of principal, but I'm not entirely sure. And the principal root is the positive root. So the square root of 25 is 5. If you want to represent both square roots of 25, you would need to write plus or minus square root 25, and then you would have plus or minus 5. Okay, so what we're going to do today is review simplifying radicals, and I suspect that you have done some of this, and then there will probably be some parts that are new. So we're going to do a bunch of examples, but they're all pretty short problems. So let's say we have the square root of 75. The point of simplifying a radical is to factor out any perfect square. So 75 is the product of 25 and 3, so the square root of 75 is the square root of 25 times 3. That's a step you're probably just going to think and not necessarily write. That is equivalent to square root 25 times square root 3. Again, you might think that step, you don't necessarily have to write it. And the square root of 25 is 5. So this simplifies to be 5 square root 3. If you were to put the original expression in your calculator and look at the decimal value, and put the simplified expression in your calculator and look at the decimal value, they should be exactly the same. And keep in mind that these are irrational, since the decimal would be non-repeating, non-terminating, and there's no way to write it as a ratio of integers. Okay, let's take a look at number 2. What we can do here, instead of multiplying 7 and 35 and getting a larger number, we can break down the 35. So we have square root 7 times square root 7 times 5. And we can think of that as square root 7 times square root 7 times square root 5. That's another step you might think without actually writing. Do you know what the square root of 7 times the square root of 7 is? Well, that would be the same as the square root of 49, and that would be 7. So we have 7 square root 5. Number 3, we have the square root of a quotient, and it is true that that is equal to the quotient of the square roots, meaning I can split it up. Both of these numbers happen to be perfect squares. The square root of 100 is 10, and the square root of 169 is 13. So our answer is 10/13. Now let's look at number 4. Like number 3, we can split this up into the square root of 11 over the square root of 144. 11 is not a perfect square, and there are no perfect square factors, so we're going to leave that as square root 11. But 144 is a perfect square. The square root of 144 is 12. So we have square root 11 over 12. Number 5, square root 27. Are there any perfect squares that are factors of 27? Why, yes indeed. 27 is 9 times 3. And what's the square root of 9? The square root of 9 is 3. So this one is 3 square root 3. Number 6. Are there any perfect squares that are factors of 98? I do believe so. 49. So 98 is 49 times 2. So you can break this down into square root 49 times square root 2, and that would be 7 square root 2. Number 7 is kind of like number 2 was. where we can break these numbers down. We could think of it as square root 150, but then you have a bigger number to break down into smaller numbers. So how about instead, if we think of this as square root 2 times 5 times square root 5 times 3, those can all go under one radical. And what's the square root of 5 times the square root of 5? The square root of 25 is 5. So we have a 5 outside the root. And inside the root we have 2 times 3, so we have square root 6. So 5 square root 6. Okay, let's do something like that on number 8. Let's break these down. You know, we could break it down all the way to primes. Let me show you a couple ways to do this. So all the way down to primes. 8 is 2 times 2 times 2, 2 cubed. 28 is 4 times 7, so 2 squared times 7. And that gives us the square root of 2 to the 5th times 7. And you could think of that as the square root of 2 squared times 2 squared times 2 times 7. What's the square root of 2 squared? 2. What's the square root of 2 squared again? 2. And then under the radical we still have the 14, 2 times 7, the ones that are left. So the answer would be 4 square root 14. That's not the only way to do it. Instead, if you break it down into perfect squares, instead of primes, you're going to have the square root of 2 times 4 times the square root of 4 times 7. Square root 4 times square root 4 is 4, so we have 4 times square root 14. So, 2 ways to do that one. Okay, now let's take a look at number 9. We have 3 square root 6 squared. So that means 3 square root 6 times 3 square root 6. Sometimes people don't square the 3, they forget about it, and they only square the square root 6. So that would not be right. So we want to multiply 3 times 3, and that gives us 9. And square root 6 times square root 6, you can say radical 6, you can say root 6, square root 6, however you like to say it. That's going to be 6, so our answer is 54. And then number 10 is similar, so why don't you give it a try, maybe pause the video, give it a try, and then check your work. 2 square root 13 times 2 square root 13, 2 times 2 is 4, square root 13 times square root 13 is 13, 4 times 13, as we all know if we like to play cards, 4 suits, 13 cards per suit, 52 cards. Okay, the next part of the lesson is called rationalizing the denominator. Rationalizing the denominator is the process that you use to simplify an expression so that there will no longer be a radical in the expression. So it's eliminating the radical. I should say there will no longer be a radical in the denominator of the expression. I might have left that word out. Eliminating the radical from the denominator. Now you've probably done this for certain problems, but not all the types that we're going to look at today. And I'm going to make this part 2 another video. So I'm going to end video 1, leave you in suspense, and in part 2 we're going to rationalize the denominator and finish this lesson.